In 4.2 and 4.3, we're going to start looking at how to go about solving polynomial equations, equations that are higher than a first degree or a second degree, but also maybe not so easy to just look at and be able to factor. Sometimes you have something that's 4 or maybe even 5 terms, and it can be factored by grouping pretty easily. You just kind of look at it and you can pull out the greatest common factor, and it works out very nicely. And then some other ones are more like what we have here, where f of x is equal to 6x cubed minus 5x squared minus 34x minus 15, and it's not a real easy polynomial to factor. And if it says solve, it wants you to find the roots. Now, you may or may not be able to graph this thing and pull out some roots. We know, because we have been doing some curve sketching, that my degree of the polynomial tells me how many times I can cross the x-axis. So I'm going to have at most 3 solutions. Now, this does not mean that they have to be 3 unique solutions. It could be 0, 0, 0. It could be 1, 1, 5. Or it could be 1, 2, 3. We'll also see later on they may not even all be real solutions, but we're not really sure yet. So if we want to start the process of solving this polynomial, we're going to use something called the rational root theorem. And what the rational root theorem says, if you take all of the factors of your constant and all of the factors of the leading coefficient. So my factors of 15 are 1 and 15, 3 and 5. 6 is going to be 1 and 6, and 2 and 3. And then one by one, you take all the factors of the constant and divide them by, individually, factors of the leading coefficient. Positive and the negative version. And this is going to be kind of like your bank of possible real solutions. It is not uncommon to get a very long list. So this list would be, I'm going to take the 1 from the 15 over, from the 15 at the constant, and divide that by every factor from 6. So 1 divided by 1, 1 divided by 6, 1 divided by 2, 1 divided by 3. The 1's been divided by everybody, so now I'll go to the 15. 15 divided by 1, 15 divided by 6, 15 divided by 2. They don't have to be nice, they just have to be a fraction. 15 divided by 3, which is 5. Now take the 3. 3 divided by 1, 3 divided by 2, 3 divided by 6. I can reduce that to a 1/2, so I don't need to write it again. 3 divided by 3 is a 1, so I don't need to write that one again. Now finally the 5. 5 divided by 1, I already have that in my list. 5 divided by 6, don't have that one yet, so 5 divided by 6. 5 divided by 2, and 5 divided by 3. And then, of course, all of these are positive and negative. So for every one that you see, you also have the negatives. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So really 26 possible real solutions. So if this guy that I graph, this f of x, I graph him, he's going to cross the x-axis. If he crosses the x-axis anywhere, it's going to be at one of these numbers. So what do you do if you want to find out which one it is? Well, we have a calculator, and so that's going to help us out a little bit. But before calculators, what you would do, you would pick your favorite one. Let's go ahead and pick 15. And you would do something called synthetically divide. So I would take the 15 and put it in the box. And then I would look at my function and make sure I don't have any skips in my exponents, meaning that I have a countdown. So 3, 2, 1, none. If I have no skips, that means I don't need to add in any zeros. So I have 6x cubed, negative 5x squared, negative 34, and negative 15. If I had a skip, like let's say I didn't have an x term, it was just 6x cubed minus 5x squared and then straight to the minus 15, I'd have to put a 0 in there. I'm going to draw a line, and then you always start the division process by dropping this first number, that leading coefficient, underneath the bar. And then what we're going to do is we're going to multiply. So it's going to be the number in the box times that number down there. So, 15 times 6 is 90, and then you're going to put that answer right in here, and then add. So a negative 5 plus 90 is 85. And then repeat. So now 15 times 85 is 1275. And 1275 plus a negative 34, I'll say minus 34, is 1241. So 1241 times 15, 18,615. Plus a negative 15, so minus 15, I get 18,600. This last number back here is what we're looking for. This will be our remainder, and it leads to two different theorems. One, the remainder theorem, because we're not creative, and the other is the factor theorem, which is a play off of the remainder theorem. So what the remainder theorem says is if you synthetically divide by a number, the remainder is the value of the function at the number that you've divided by. So what this example would show is that if I were to take 15 and plug that into 6x cubed minus 5x squared. Let me fix my coefficients. There we go. Cube 15x squared minus 34 times 15, then minus a 15, I will get out, and 18,600. And that's pretty easy to go ahead and check. What you're specifically looking for, if you're looking to solve, is for this guy to be a 0. Because that means if you plug the number in the box into the equation, that x value that you plug in is going to lead to a y value of 0. And if you have an x value, I'll just go ahead and say 2, and then a y value of 0, well, that means you're right on the x-axis and you found yourself a solution. So this clearly didn't work. 15 is not a factor, and so it can't be a solution. He would come out of the pot, and then you would pick another one and keep doing this. Well, we don't have all day, so what we're going to do is go to our calculator, and we are going to plug in our function so that it can give us a starting point. And I'm not really concerned with being able to see the graph. I don't really care really what the graph looks like. I care about the spots that I'm crossing the x-axis. So I have something right around like a negative 2-ish. This looks like maybe a negative half. And then I have this 3 that looks like a nice solid 3. So you want to find one, preferably a nice one, that you can synthetically divide by, and we could start to break this down. So you could either use second calc 0, or you can go into your table and just look for where's my y value is 0. Oh, right here at the 3. So that means 3 is a factor. So when I synthetically divide by 3, my last number, that remainder, is going to be a 0. So let's do that now. 3 goes in the box, and then it's 6, negative 5, negative 34, negative 15. Drop the first number under the bar. 3 times 6 is 18. Add down. Multiply. 13 times 3 is 39. Add down. How convenient. 3 times 5 is 15. Add down, and I get a 0, and that's good news. That means that 3 is a solution. So the factor theorem says if your remainder, I'm going to use an R, is equal to 0, then the x value in the box is a solution. And remember, you're a solution if, in this case, that's where you're going to cross the x-axis, so x equals 3. That also means that x minus that number in the box would then have to be equal to 0, and then that is a factor. So x minus 3 is equal to 0, right? Because when we were solving, like using quadratic formula, or when we were factoring, we would have these two numbers, and we'd say, oh, well, maybe you're equal to 0, and then we would solve. So maybe something like x minus 3 is equal to 0. Add 3 to both sides. 3 is the solution. This goes backwards. It verifies the solution using the factor theorem by looking for the 0 and the remainder, and then say, oh, let me move you to the other side, and now I have a factor. Now I can take that factor and say, well, x minus 3 times my quotient down here. So this factor up here times this, like what we did before when we were just dealing with the numbers, is going to be a partially factored form of the original. This is my remainder. This is my constant. This is the coefficient of x. This is the coefficient of x squared. And if I had another, it would be x cubed and x to the 4th. And you count up, and you always count up in order. So this expression, the 6, 13, 5, 0, well, 0 is a remainder. He goes. That's a positive 5. This is a positive 13x. And this is a positive 6x squared. And this is another way to say the f of x that I have listed right here. It's just we're ignoring the variables because we know that they're going to count up in order. So now he looks a little bit better. And I'll show you what I'm talking about. If I go into here and I put in x minus 3 times 6x squared plus 13x plus 5 and hit graph. So here comes the first one, and there goes the second one, and you didn't see it because they're exactly the same. So my y2 is a partially factored form of y1. So at this point, usually if you can break it down where you have one linear, right, first degree, and a quadratic, now this part I should be able to factor on my own, maybe, right? So I'm looking for factors of 5 and factors of 6, so that when they multiply, when I multiply them and add them together, I get a 13. You can, if this is something, factoring is still tough, you can go back to the big list that we had up here and say, well, we already used the 3, so he's out. I used him up. Let me pick another one. Oh, like maybe the negative 1/2, because that's what it kind of looks like I might have on my graph that I have. Or maybe you're okay with factoring and say, oh, I know. This is a 5 and a 1, and this is a 2 and a 3, maybe a 6 and a 1, but 2 times 5 is 10, plus 3 more. Would give me what I'm looking for the 13, right? I would have 2, times 3. That would be a 6x squared. My outer would be a 10x. My inner would be a 3x. That's 13x. And then 1 times 5, 15. And so now I'm completely factored. I already know this solution. He's x equal to 3. 2x plus 1 is equal to 0. I'll subtract the 1. Divide by 2. There's that negative 1/2. The other one, 3x plus 5 is equal to 0. Subtract the 5. And divide by 3. And negative 5/3 and a negative 1/2. I'm going to scroll back up to the top. And there they are. So if you have real solutions, it has to come out of this list. In the next video, we'll look at what happens when they're not real.